Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you're out walking the dog right now or, maybe driving home in the dark, take a second to look up at the night sky.
It's a good night for it.
Right. And for decades, science has offered us this rather cold, bleak promise about how that sky, and honestly, reality itself wraps up.
Yeah, a scenario known as the Big Freeze.
Exactly. The universe simply expands, just forever. Galaxies drift so far apart that the night sky eventually goes completely black.
Which is pretty terrifying to think about.
It is. Stars burn through their fuel, they flicker out, and everything slowly, inevitably reaches absolute zero. It's just this endless, empty, frozen expanse.
It really is the ultimate definition of fading to black. A quiet, lonely end.
Yeah.
And that's dictated by the assumption that the expansion of the universe is on this unstoppable, exponential runaway trajectory. For a very long time, that was the accepted, undisputed destiny of our cosmos.
But what if the engine driving that endless expansion is, running out of gas?
That is the big question right now.
Right, because what if the universe isn't coasting toward a quiet freeze, but is actually setting us up for something entirely different?
Something much more dramatic.
Exactly. We are unpacking massive, foundation-shaking observations from the years 2025 and 2026. Cosmologists have been looking at dark energy, the mysterious force dominating our universe, and they've uncovered stunning new evidence that this force is actively weakening.
And the implications of a weakening dark energy, they cannot be overstated. We are talking about a fundamental shift in our understanding of the fabric of space-time.
It's huge.
If this holds, we have to rewrite the entire cosmological narrative.
We are going to explore the massive cosmic maps that revealed the secret, look at the actual physics of space-time to understand how a vacuum can actually lose its repulsive power.
Which sounds impossible, but we'll get there.
Right, and we'll discover how the ultimate destiny of our universe might have just flipped. We might be looking at a shift from that eternal freezing dilution to an eventual catastrophic compression.
Or, depending on how the data shakes out, something even more violent.
Which we will definitely get into. I want to treat this like an incredible secret about the very code of reality that has just been discovered, because you absolutely need to hear this. But before we look at the weakening, we have to establish the baseline.
With status quo.
We need to talk about what this force is, or at least what the textbook definition has been since the late 1990s. Dark energy makes up roughly 70% of the universe's total energy content.
Right. All the matter we understand, the stars, the galaxies, the planets, you, me, the device you are listening to this on, that all makes up less than 5% of the universe.
It's such a tiny fraction.
It really is. And another 25% is dark matter, which exerts a gravitational pull but doesn't interact with light.
And then there's the rest.
Exactly. That massive remaining 70% is dark energy.
And it was discovered back in 1998, right, through observations of distant supernovae.
Yeah, type Ia supernovae specifically.
Okay, let's unpack this, because those exploding stars act as our standard candles.
Right, exactly. A standard candle in astrophysics is basically an object whose absolute luminosity is known.
So we know exactly how bright it really is.
Precisely. Because we know exactly how much light a type Ia supernova produces when it detonates, we can measure how dim it appears from Earth to calculate exactly how far away it is.
Like looking at a street lamp down a long road.
That's a perfect way to think about it. In the late 90s, 2 independent teams of astronomers were looking at these distant explosions.
And they were expecting something completely different than what they found.
All right. Oh, completely. They fully expected to see that the expansion of the universe was slowing down. They assumed the cosmos was, exhausted from the initial outward push of the Big Bang.
Like it was running out of momentum.
Yeah, and that the collective gravity of all the matter in the universe was acting like a brake pedal, just pulling everything back together.
But instead, they found the brake pedal wasn't being pushed at all.
Not even a little bit.
The universe was stepping on the gas. The expansion was accelerating, just flying apart faster and faster.
Because the supernovae were dimmer than they should have been, which meant they were further away than the steady expansion models predicted. Space itself was stretching at an accelerating rate.
Which is just wild to think about.
It really threw everyone for a loop. To explain this, cosmologists basically resurrected an old concept from Albert Einstein, the cosmological constant.
The famous blunder.
Right. Einstein originally proposed it as an energy intrinsic to empty space itself. It was just a mathematical patch to keep his model of the universe static.
Because he didn't want the universe to be expanding or contracting?
Exactly. He later called it his biggest blunder when Hubble discovered the universe actually was expanding. But in 1998, that blunder became the dark energy that pushes the universe apart.
But crucially, the cosmological constant was assumed to be, well, exactly that, a constant.
Unchanging over time, unchanging across space.
You know when you wake up and your phone has updated its operating system overnight without asking you?
Oh, I hate that.
Right. And suddenly the interface is different, and half your apps don't work right. Well, for 25 years, scientists essentially thought this dark energy code, like the physics engine driving the universe's expansion, was hardwired.
Baked right into reality.
Exactly. It was permanently fixed at the very bottom of reality source code. You just don't question it. But with this new 2025 and 2026 data, it looks like the cosmos is pushing an unprompted software update.
And it's crashing the standard models.
The code is actively rewriting itself as the simulation runs. The cosmological constant might actually be a variable.
And the astrophysics community is in a state of shock over this. Because the lambda CDM model, where lambda stands for this exact cosmological constant, is the bedrock of modern cosmology.
It's the foundation of everything.
It is. It beautifully explains the cosmic microwave background, the distribution of galaxies, the abundance of light elements. Every single calculation we have ever made about the future of the cosmos relies on dark energy being a steady, unchanging property of empty space.
So if it's not steady,
if dark energy is evolving, if that foundational code is rewriting itself, our universe is far more chaotic on the grandest scales than we ever dared to imagine.
But we didn't just stumble onto this software update by accident. I mean, you don't just look up at the sky and notice the universe is behaving differently today than it did yesterday.
No, you need incredible technology for that.
Right. Uncovering a shift in something as fundamental as dark energy required mapping reality on a scale that had literally never been attempted before. The map makers of the universe are the ones who spotted the glitch.
And you're referring to the Dark Energy Spectroscopic Instrument, known as DAI.
Yeah, DAI, down in Arizona.
Right, mounted on the Mayall telescope. This instrument is just an absolute marvel of modern engineering. It doesn't just take pictures, it captures the spectra of millions of distant objects.
And the way it does this is so cool.
The focal plane of the telescope is packed with 5,000 tiny robotic fibers.
5,000.
5,000. Each one of those robotic eyes independently positions itself to capture the light from a single specific galaxy or quasar.
5,000 robotic eyes shifting and locking onto targets billions of light years away, mapping the universe in 3 dimensions.
It's breathtaking.
And they aren't just logging where a galaxy is in the sky, right? They are logging its redshift.
Yes, and redshift is the key to the 3rd dimension. As the universe expands, the space between us and a distant galaxy stretches. The light traveling from that galaxy gets stretched along with the space, pushing its wavelength toward the red end of the spectrum.
Like a Doppler effect, but for light in stretching space?
Exactly like that. By measuring exactly how much the light has redshifted, DSI determines how fast the universe was expanding at the exact moment that light began its journey.
So it's a time machine.
Essentially, yes. DSI mapped galaxies and quasars stretching back more than 11 billion years.
The universe is roughly 13.8 billion years old. So DSI is looking back through the vast majority of cosmic history.
Catching light that left its source long before our solar system even formed.
And the timeline of what they found is fascinating. Like in 2024, the DSI collaboration released their first year of data, and there were already these tentative whispered hints that the influence of dark energy wasn't staying steady.
But nobody wanted to jump the gun.
Why is that?
Because statistical flukes are the bane of observational astronomy. When you are dealing with millions of data points, patterns can emerge purely by chance.
Like seeing shapes in the clouds.
Right. But by early 2025, they had more than double the data analyzed. The map was richer, deeper, and stretching further back in time.
And those hints didn't fade away into statistical noise?
No, they crystallized.
Oh.
When they combined the comprehensive DSI map with measurements from those type Ia supernovae and the cosmic microwave background radiation, the departure from the standard lambda CDM model hit an astonishing milestone.
The 4.2 sigma shift.
Yes. It reached around 4.2 sigma significance in some of the analyses.
Okay, let me stop you right there because 4.2 sigma sounds massive. A 4.2 sigma result means the chance of this being a random statistical artifact is like less than 1 in 30,000.
It is extremely unlikely to be a fluke.
Right. In medicine or biology, if an experimental drug worked with a 1 in 30,000 chance of being a fluke, they'd be throwing a parade and printing the textbooks right now. The math is absolutely screaming at us that dark energy is changing. So why the hesitance? Are physicists just, I don't know, too stubbornly attached to Einstein's cosmological constant to admit lambda is dead?
What's fascinating here is it is not stubbornness. It is an acute awareness of how incredibly difficult it is to measure the universe.
Fair enough.
The 4.2 sigma tells us the math is solid based on the data provided. The fear is that the data itself contains systemic errors.
Right.
Astronomy is incredibly messy. We are looking through billions of light years of interstellar dust, which can absorb blue light and make a distant supernova look redder and dimmer than it actually is.
Like looking through a dirty windshield.
Exactly. If our models for how dust behaves are slightly off, it artificially changes our distance calculations.
So a speck of dust on the cosmic camera lens could mimic the signature of weakening dark energy.
That is one potential trap, yes. We also have to account for galaxy bias. We assume galaxies cluster in regions where invisible dark matter is densest.
Okay.
But what if the types of galaxies DESI observed, say massive luminous red galaxies, preferentially form in slightly different environments than we model?
Then the map is skewed.
Right. Or consider the supernovae themselves. We assume a Type I supernova today explodes with the exact same physics as one that exploded 10 billion years ago.
Do they?
We think so. But the early universe had fewer heavy elements, less metal. Does a metal-poor star explode slightly differently than a metal-rich one?
I see.
If we misunderstand just one of these tiny, subtle astrophysical factors, it introduces a systemic bias that looks exactly like a 4.2 sigma discovery of new physics.
That is so tricky. And we've seen false alarms before, right? Telescopes have registered massive anomalies that just vanished the moment someone recalibrated a sensor.
Exactly. Caution is mandatory.
But even with that necessary caution, you just can't ignore the math. The data strongly points to a change.
It really does.
So if we accept the 4.2 sigma result, we have to look at what is actually happening to the fabric of space-time. We need to understand the mechanics of this fading force. Like, how does a vacuum actually lose its push?
To understand the fading, we must deeply understand how the constant worked in general relativity to begin with. In the standard picture, dark energy has a constant energy density.
Density meaning the amount of energy in a given space.
Yes, density is simply the amount of energy in a specific volume of space.
So let's use an analogy to make this mechanism concrete for you listening. Imagine you have a magical cup of coffee.
Okay, magical coffee.
Yeah. In the standard model of cosmology, as this cup magically expands, say it grows from the size of a standard mug to the size of a massive auditorium, the coffee inside magically multiplies to keep the cup completely full at the exact same strength and temperature.
A very strong cup of coffee.
Exactly. The density of the coffee never changes, even though the volume is exploding. As the universe expands, we get more space, and magically more dark energy just appears to fill it at the exact same density.
That magical multiplication is the heart of the cosmological constant, and it comes down to a concept called the equation of state parameter, denoted by the letter W.
The letter W.
Yes. This parameter is the mathematical ratio between the pressure of a substance and its energy density.
Okay. Pressure and density.
Right. For normal matter, like the chair you're sitting on, the pressure is virtually zero compared to its massive energy density. So W is zero.
Makes sense.
For radiation, like photons of light bouncing around, W is exactly 1/3.
But dark energy is different. It requires a bizarre equation of state to do what it does.
It requires an equation of state of exactly -1. W equals -1. This means the dark energy vacuum possesses a tremendous inherent negative pressure.
Negative pressure, like a stretched rubber band where the tension pulls inward.
Yes.
But wait, if negative pressure pulls inward, why does dark energy push the universe apart? That feels backwards.
That is the beautiful counterintuition of general relativity. In Newton's gravity, only mass creates gravitational pull. But in Einstein's universe, energy, mass, and pressure all warp spacetime. They all contribute to gravity.
So pressure creates gravity.
Yes. And because the negative pressure of the vacuum is so immense conceptually, it is equal and opposite to its energy density. It dominates the equation. In the mathematics of the stress-energy tensor, a sufficiently massive negative pressure actually generates a repulsive gravitational effect.
It actively pushes space outward.
It does. And because W is exactly -1, as you pull the cosmos apart, the tension remains exactly the same. The magic coffee stays strong.
But the DSI data from 2025 and 2026 suggests the magic is fading. The data indicates that dark energy was stronger in the early universe and has been steadily losing strength over the more recent billions of years.
The equation of state parameter W is not -1 anymore.
It is creeping upward, becoming less negative over cosmic time.
Right. If WON shifts from -1 to, say, -0.9 or -0.8, the negative pressure is dropping. The tension in the vacuum is relaxing.
So going back to the auditorium-sized cup, as the cup grows, the coffee isn't multiplying perfectly anymore. It's getting watered down, the density is dropping, and the outward push is weakening.
Taking your analogy a step further, it's as if the underlying mechanism generating the coffee is slowly losing power. The repulsive gravitational effect diminishes.
Which changes everything.
It does. And if that anti-gravity push slows down, we enter a monumental cosmic tug-of-war because the standard attractive gravity hasn't gone anywhere.
Right. All the matter in the universe, every galaxy cluster, every supermassive black hole, the vast invisible webs of dark matter has mass. And that mass is constantly trying to pull the universe back together.
It's relentless.
For the last 5 billion years, dark energy has been winning that tug-of-war effortlessly. But if dark energy is watering down, if it's losing its negative pressure, the immense gravity from all the matter in the universe might actually regain dominance.
The brake pedal is finally catching while the accelerator runs out of gas. If gravity starts winning that tug-of-war, the entire fate of reality fundamentally changes. The timeline of the universe fractures into entirely different apocalyptic paths.
Which brings us to the branching path of cosmic destinies. Let's contrast the old fate with the new possibilities, because the contrast is stark. We established the old fate at the beginning, the big freeze.
The long, cold fade.
Right. Under the standard model where dark energy remains constant at -1, the universe expands forever. The space between galaxies grows so vast that eventually, light from one galaxy can never reach another. The universe becomes a collection of isolated, dying islands, cooling to absolute zero.
But if dark energy is weakening, as the new data suggests, we move from the big freeze to the big crunch.
And the big crunch is an entirely different thermodynamic beast.
Completely different. If the acceleration eases, the expansion will eventually coast, and then gravity will seize control, the expansion will reverse.
Just stops and turns around.
The cosmos will reach a maximum size. Some calculations based on the DSI data suggest that maximum size could be reached roughly 11 billion years from now.
11 billion years. I mean, our Earth is about 4.5 billion years old. The universe is 13.8 billion years old. 11 billion years from now is not some infinitely distant eternity.
That's really not.
It's less than the current age of the universe. It's a tangible, approaching horizon.
And after it reaches that maximum volume, the universe begins to contract. It shrinks. The cosmic expansion reverses into a catastrophic collapse, ending in a crunch perhaps 20 billion years after the turnaround.
Here's where it gets really interesting. I want you to think about what that timeline actually looks like. Fulfilling the big crunch flips the script entirely. We go from a future of eternal dilution, where everything quietly fades, to a future of eventual, overwhelming compression.
Exactly.
Galaxies won't be drifting away, they will start rushing toward each other. And it's not just space getting smaller.
It's the entire thermodynamic history of the universe playing in reverse, but with massively increased entropy and chaos.
That sounds intense.
It is. Right now, the cosmic microwave background, the afterglow of the Big Bang, is a faint, freezing wash of microwaves. But as the universe contracts, that background radiation gets compressed. It blue shifts. The wavelength of the ambient light gets shorter and more energetic.
So the empty space between stars stops being cold. It actually starts to warm up.
Exactly. Empty space gets hotter and hotter. Eventually, the ambient temperature of the universe exceeds the surface temperature of the stars.
Wait, the space around the stars becomes hotter than the stars themselves.
Yes. And at that point, stars can no longer radiate heat outward into space. They literally begin to cook themselves from the outside in, exploding or violently collapsing.
Oh, wow.
Vast galaxy clusters smash into one another. Supermassive black holes at the centers of these galaxies merge, releasing tidal waves of gravitational energy. Finally, all matter and radiation are crushed into an unimaginably dense, hot singularity. The universe basically eats itself.
It is apocalyptic in the truest sense of the word.
The very loud end.
But wait, we have to look at the other side of the variable. We discussed the W parameter changing from -1 up towards 0, right? What if it changes in the opposite direction? What if it drops below -1?
That is the realm of what physicists call phantom energy.
Phantom energy.
If W is less than -1, the dark energy doesn't just stay constant or watered down. Its density actually increases as the universe expands. It is a runaway, escalating feedback loop. This scenario is known as the Big Rip.
So the magical coffee doesn't just stay strong, it becomes hyper-concentrated and violently expansive the bigger the cup gets.
Yes. And the repulsive force grows so unimaginably powerful that it eventually overpowers every other fundamental force in nature. It's a timeline of progressive dismantling.
Progressive dismantling, what does that look like?
First, the phantom energy overpowers the gravity holding the largest structures together. Massive galaxy clusters are torn asunder. Millions of years later, the dark energy density grows so high it overpowers the gravity holding individual galaxies together.
So the Milky Way is stripped apart.
Yes, its stars are flung out into the void.
Then it comes for the solar systems.
It overcomes the gravity of local star systems. Planets are ripped away from their orbits. But the density of phantom energy keeps climbing. Months before the ultimate end, it overpowers the electromagnetic force holding macroscopic objects together.
So planets just shatter.
Planets themselves shatter and explode. And in the final fractions of a second, the phantom energy overcomes the strong nuclear force. The very space inside an atom stretches so violently that atomic nuclei are shredded.
Protons and neutrons just pulled apart.
Finally, subatomic particles themselves are torn apart. Space expands at an infinite rate. No structure, no matter how microscopic, can hold together.
A universe shredded at the subatomic level. A literal tearing of the fabric of reality.
It's a sobering thought.
Where does the current 2025 and 2026 data actually point, though? Are we heading for the crunch or the rip?
If we connect this to the bigger picture, the day's eye results definitely lean toward the weakening scenario, the path toward the crunch, or at least a less extreme freeze. However, because our measurements still have margins of error, and because different astrophysical datasets pull in slightly different directions, the terrifying extreme of a big rip remains mathematically possible.
We absolutely cannot rule it out.
We cannot.
To figure out exactly which apocalypse is coming, cosmologists didn't just rely on Day's Eye's galaxy map. If dark energy is actually watering down, it shouldn't just show up in how fast galaxies are moving away. It should fundamentally alter how matter clumps together over billions of years.
Right.
That's exactly what the Dark Energy Survey, or DES, spent 6 years looking for.
And the Dark Energy Survey released its final comprehensive analysis in early 2026. It was a monumental, independent effort designed to cross-examine the standard model.
They threw everything at the wall.
They really did. For the first time, a single experiment combined multiple, completely distinct methods of measuring the universe to get immensely tight constraints on the behavior of dark energy.
So what were the methods?
They combined weak gravitational lensing, galaxy flustering, supernovae, and baryon acoustic oscillations.
Okay, baryon acoustic oscillations, or BAO. We have to dive deeply into this because it is just one of the most elegant concepts in astrophysics. We are using literal sound waves frozen from the dawn of time as a cosmic ruler.
It sounds like science fiction.
It really does. How does a sound wave freeze?
Well, we have to travel back to the first 380,000 years after the Big Bang. The universe was completely different. It wasn't full of empty space and stars. It was a phenomenally hot, dense plasma.
Like the inside of a star.
Exactly. A soup of protons, electrons, and photons of light, all smashed together. It was so hot that light couldn't travel. Photons were constantly bouncing off the free electrons.
So the universe was basically an opaque, glowing fog.
Inside that glowing fog, two massive forces were battling. Gravity was trying to pull the matter together into dense clumps. But the photons, the light, exerted an intense outward radiation pressure, pushing the matter back apart.
Like a pot of boiling water.
Right. This epic struggle between gravity pulling in and radiation pushing out created literal pressure waves, sound waves. These massive acoustic ripples traveled through the plasma at over half the speed of light.
Acoustic ripples the size of galaxies, just rolling through a universe-wide ocean of plasma.
Then, about 380,000 years in, the universe expanded and cooled just enough for a profound phase transition. It cooled to the point where the protons could finally capture the electrons and form the first stable neutral hydrogen atoms.
And this moment is called recombination.
Recombination, yes. Because the electrons were suddenly locked up in atoms, the photons of light were free to travel unobstructed. The fog lifted. The universe became transparent.
And that flash of free light is what we now see as the cosmic microwave background.
Exactly.
But what happened to the sound waves?
Well, without the radiation pressure from the photons, the outward push driving the sound waves instantly vanished. The acoustic ripples literally froze in place.
They just stopped.
They stopped.
Yeah.
Wherever the peak of a sound wave was at that exact moment of recombination, it deposited a slightly denser ring of matter. Over the next 13 billion years, those denser rings of matter exerted slightly more gravity, pulling in dark matter and gas, and eventually sparking the formation of galaxies.
So today, if we look out at the universe, there should be a slightly higher probability of finding galaxies separated by the exact distance that those sound waves traveled before they froze.
Exactly. That distance, known as the sound horizon, is roughly 150 megaparsecs, or about 500 million light years in today's universe.
That is a massive ruler.
It is. And because we know the exact physics of the early plasma, we know exactly how big those frozen rings should be. By looking at how large those 500 million light-year rings appear to us from Earth in different depths of space, we can calculate precisely how the universe has expanded over time. BAO is the ultimate standard ruler.
So DES combined this frozen sound wave ruler with weak gravitational lensing. Let's explore the lensing, because if BAO is listening to the echoes of the early universe, weak lensing is looking through the funhouse mirrors of the modern universe.
I love that comparison. Weak gravitational lensing maps the invisible skeleton of reality. We know dark matter makes up 25% of the universe. It forms massive, invisible halos and filaments.
But we can't see it.
We can't see it, but its immense mass bends the fabric of space-time. When light from a distant background galaxy travels toward Earth, it has to pass through these warped regions of space. As it does, the path of the light is deflected.
So the image of the background galaxy gets stretched and distorted by the invisible mass in front of it.
Yes. The distortions are incredibly subtle, maybe a 1% change in the apparent shape of a galaxy. That is why it's called weak lensing.
Because it's so faint.
Right. But by using advanced statistical algorithms to measure the tiny correlated distortions in the shapes of hundreds of millions of background galaxies, the DES team was able to reverse engineer the precise location and density of the invisible dark matter foreground. They mapped how matter clumps together.
They map the clumpiness of the universe.
Exactly.
And this is where the plot thickens. When DES combined the BAO standard ruler, the exploding supernovae, the galaxy clustering, and the weak lensing funhouse mirrors, the results were deeply provocative. They were broadly consistent with the standard lambda CDM model, but they fit the evolving, watering down dark energy models almost equally well.
It was a statistical stalemate.
So wait, we threw everything at this lensing, clustering, exploding stars, and the results are basically saying it could be the standard model, but it could be evolving. That sounds incredibly frustrating, like a massive stalemate.
It does sound frustrating, I know, but it's actually thrilling.
Thrilling.
Yes, because buried inside that DES dataset was an amplification of a major crisis in cosmology, the S8 tension.
The S8?
The S8 tension is the loose thread that might unravel the entire standard model. S8 is a specific parameter that quantifies the clumpiness of matter in the universe. How tightly is the cosmic web woven?
Okay, S8 is clumpiness.
Right. Now, we have two very different ways to measure this. The first is to look at the early universe. We use satellites like Planck to observe the cosmic microwave background, that flash of light from recombination.
The frozen sound wave era?
Exactly. We measure the tiny temperature fluctuations in that light, calculate the density of the early universe, and then use the standard lambda CDM model to fast forward 13.8 billion years to predict how clumpy the universe should be today.
So the standard model insists that given the starting conditions, the modern universe should be heavily structured. It predicts a high S8 value. The universe should be very chunky.
But the second way to measure S8 is to actually look at the modern local universe right now. That is exactly what DES did with its weak lensing map.
And then what did they find?
When DES measured the local universe, it found an S8 value that was significantly lower than the Planck prediction. The modern universe is smoother, less clumpy, and less tightly bound than the standard model insists it must be.
So the matter simply hasn't grouped together as densely as the unchanging dark energy model predicts.
Exactly. And it isn't just the clumpiness. There is a second crisis. The Hubble tension.
The Hubble tension, that's about the expansion rate, right?
Yes, the Hubble tension involves the actual rate of expansion today, known as the Hubble constant. Again, if we take the early universe data from the cosmic microwave background and fast forward using the standard lambda CDM model, it predicts a specific expansion rate.
Let me guess, the modern measurement doesn't match.
It doesn't. When we measure the local universe using standard candles like Cepheid variable stars and supernovae, the local universe is expanding significantly faster than predicted.
So the early universe and the late universe violently disagree with each other on how fast space is stretching and how tightly matter is clumping.
Yes, and for years, scientists hoped these tensions were just measurement errors. Maybe Planck had a calibration issue, or the local supernova maps were skewed by our position in a local cosmic void.
But the DES data in 2026 confirms the tensions are real.
They are getting more pronounced. The standard model is breaking.
And this is exactly how a watering down dark energy provides a magnificent, elegant solution. If dark energy is not an unchanging cosmological constant, but is instead a dynamic, evolving force, say, it was stronger in the distant past and is steadily losing its negative pressure today, it entirely alters the growth of structures.
It fixes the math. If the repulsive push was stronger in the past, it would have suppressed the ability of gravity to pull matter together early on, resulting in a smoother, less clumpy universe today.
Perfectly matching the low S8 value from DES.
Concurrently, an evolving dark energy that changes its equation of state over time fundamentally alters the expansion history, bridging the gap between the early universe predictions and the fast local expansion rate.
So an evolving dark energy is the exact missing puzzle piece needed to solve both the S8 tension and the Hubble tension simultaneously.
Yes, the standard model is failing because it assumes the physics engine is running on a rigid, unchanging code. The moment you introduce a variable, the moment the dark energy updates, the entire simulation suddenly perfectly aligns with our observations.
It's a profound realization. This frustrating anomaly, this 4.2 sigma glitch in the map, isn't just a headache, it's the universe handing us the key to a much deeper layer of reality.
That's a beautiful way to put it.
And this concept of a shifting, dynamic, dark energy isn't entirely new. Some theoretical physicists have been waiting decades for observational astronomy to catch up to their math. This shifts the entire conversation into the realm of theoretical physics and string theory.
Oh, the string theorists are undeniably thrilled by the 2025 and 2026 observational data.
I bet.
String theory is a framework that attempts to reconcile general relativity with quantum mechanics, but it is notoriously difficult to test observationally.
Because the strings are so small.
Exactly. Now, however, the astronomical data might be stepping directly onto their turf. In certain string theory frameworks, the gradual weakening of dark energy isn't an anomaly. It is a natural, predicted outcome of physics beyond the standard model.
Let's break down how string theory actually predicts a fading vacuum. We have to look at the extra dimensions. In string theory, the fundamental ingredients of reality aren't tiny zero-dimensional particles. They are one-dimensional vibrating strings of energy.
Right.
But the mathematics of string theory only functions if the universe contains more than the familiar 3 dimensions of space and 1 dimension of time.
Depending on the specific framework, string theory requires 10 or 11 total dimensions.
10 or 11.
Yes. We obviously only experience 3 spatial dimensions. The theory posits that the extra 6 or 7 spatial dimensions are compactified.
Compactified, meaning they're crushed down.
They are curled up into microscopic, incredibly complex geometric shapes, often referred to as Calabi-Yau manifolds, that are so vanishingly small we cannot directly observe or interact with them.
They exist at every single point in our 3D space, but they are wrapped up at the quantum level.
Yes.
But how does a microscopic curled-up dimension affect the colossal push of dark energy across the entire observable universe?
In these frameworks, the physical constants of our macroscopic 3D world, the mass of an electron, the strength of gravity, and crucially the vacuum energy of empty space, are entirely determined by the precise geometry, size, and topology of those hidden compactified dimensions.
Wow.
Dark energy isn't just a random number assigned to our universe. It is a dynamic manifestation of the shape of the extra dimensions.
So if the geometry of those extra dimensions changes, the vacuum energy in our 3D world changes.
Precisely. As our macroscopic universe expands and cools over billions of years, those hidden extra dimensions aren't necessarily frozen. They can subtly shift. They can slowly expand or relax their topological tension.
And as they relax?
As the hidden dimensions relax, the amount of dark energy they project into our visible 3D universe decreases. The vacuum loses its repulsive power.
The weakening of dark energy across billions of light years might literally be the macroscale echo of microscopic hidden dimensions shifting their geometry. That is a staggering concept.
It is elegant. When the DSI data and the DS weak lensing maps are analyzed within these string theory frameworks, they actually fit the observations better than Einstein's simple cosmological constant.
The data strongly suggests that dark energy is dynamical. It points toward the existence of what physicists call scalar fields.
Yes, scalar fields driving a concept called quintessence.
Quintessence.
Quintessence is the idea that dark energy is a dynamic, time-varying, spatially dependent quantum field that permeates all of reality. It is a living, evolving entity, not a dead mathematical constant.
So what does this all mean? If I'm listening to this right now, trying to wrap my head around 11-dimensional manifolds and quintessence, the natural question is, why does a time-varying scalar field matter to us?
It's a fair question.
Beyond the theoretical math, this forces a complete revision in how we view reality itself. It proves the universe isn't a static, unfeeling machine with fixed gears. It's an evolving ecosystem. And on a practical level, it throws a wrench into every discipline of astrophysics.
This raises an important question because every distance we've calculated, every structure we've modeled, rests on the assumption of a rigid ruler.
And if the ruler is made of rubber, everything shifts.
Everything. If we are using gravitational wave astronomy to measure the collision of two black holes halfway across the universe, we calculate their distance based on the standard expansion model.
But if dark energy is weakening,
those black holes might be significantly closer or farther away than we realized. We have to recalculate the mass, the energy, and the timeline of every major cosmic event.
we are sitting at a cosmic crossroads. The 70% of the universe that dictates our destiny is a complete mystery, actively changing its behavior. Is it a property of empty space? Is it the gravity of extra dimensions? Is it a new fundamental scalar field? We know it's watering down, but we are still fundamentally blind to its true nature.
But thankfully, the wait for definitive answers won't take billions of years. We are transitioning into an era where observational astronomy is deploying instruments powerful enough to finally corner this ghost.
Because the ambiguity surrounding the 4.2 sigma result and the systemic errors will not last long, we are on the precipice of overwhelming clarity.
We really are. Future observations are gearing up right now to settle the nature of dark energy permanently. The Vera-C-Rubin Observatory and the Euclid Space Telescope are the vanguard of this new era.
The Vera-C-Rubin Observatory, conducting the Legacy Survey of Space and Time, or LSST, is a technological monster.
It's unbelievable.
It is stationed in Chile, and it features the largest digital camera ever constructed, over 200 megapixels.
And it isn't just taking static pictures.
Right. It is going to scan the entire visible southern sky every few nights, continuously, for 10 solid years. It is essentially filming a decade-long, high-definition motion picture of the universe.
It will catalog tens of billions of galaxies, mapping their positions, their weak lensing distortions, and tracking millions of supernovae.
Just a tidal wave of data.
By observing the cosmos in motion, it will provide a dataset so vast and deep that any statistical anomalies, any systemic dust errors, or galaxy bias will be ironed out by sheer volume.
And then there's Euclid.
Yes, concurrently, the Euclid telescope is operating in space, free from the blurring effects of Earth's atmosphere. Euclid is specifically designed to map the dark universe with unprecedented precision, measuring the redshift and shape of galaxies over a massive swath of cosmic history.
It's incredible to think about. The universe's expansion might be decelerating, but our technological capacity to discover its secrets is accelerating exponentially.
Beautifully said.
Within the next few years, we will know with absolute irrefutable confidence if dark energy is truly evolving. We will know if the whispers from 2025 and 2026 were the dawn of a new era in physics, or just the most complex systemic illusion ever recorded.
And we have to remember, the scientific method demands rigor. Cosmologists will not throw away Einstein's cosmological constant, a pillar that has stood for over a century, without overwhelming proof from multiple independent observatories.
The standard model is robust, and replacing it requires a flawless alternative.
Exactly. But as an observer of this field, the prospect that the engine driving the cosmos is running out of fuel is the most tantalizing revolutionary puzzle in modern science. We might be the exact generation of humans that discovers the universe has a distinct narrative arc, a changing character, and an expiration date radically different than the one we were taught.
We started today with a universe that seemed locked into a cold, inevitable trajectory. The Big Freeze was a steady, predictable march toward infinite nothingness.
That was the promise.
But thanks to the microscopic precision of the DI robotic fibers and the vast multidimensional funhouse maps of the DARP Energy Survey, we now see a universe that is intensely dynamic and dramatically uncertain. The 70% of reality that we thought was a stable foundation might be actively losing its grip.
And as it loses its grip, the balance of power in the cosmos shifts. Gravity, the silent patient force pulling from the center of every galaxy, is poised to take the reins.
The story pivots from endless expansion toward the monumental contraction of the Big Crunch, or perhaps, if the field fluctuates wildly, toward the tearing chaos of a Big Rip.
Both are on the table.
But I want to leave you with one final, lingering thought to mull over, a philosophical implication that builds on the theoretical physics we just discussed. We explored the idea of quintessence, that dark energy is tied to dynamic, living scalar fields that evolve, relax, and fade over billions of years. We know this field is currently awake, dominating the universe, but slowly watering down.
It is actively evolving as the ambient temperature and density of the universe drop.
But if the vacuum of space is a complex quantum ecosystem where one monumental field can slowly weaken and fade, what else is asleep in the dark?
That is a chilling thought.
If the conditions of the universe change enough over the next 11 billion years to shut down dark energy, could reaching that new, colder environment act as a trigger? Could another, completely unknown fundamental field suddenly wake up in the freezing void to dictate the next chapter of reality?
The diagnostic landscape of reality is entirely murky, rewriting its own rules in real time.
The absolute end of everything might not be a freeze, a crunch, or a rip. It might just be the catalyst for a force we haven't even named yet. The universe remains beautifully, unsettlingly incomplete. The quiet freeze is off the table, and the real cosmic adventure has just begun. Keep looking up.